Hey everybody, today's lesson is on solutions. Particularly today I'm going to look at what are known as, I'm going to explain to you how solutions form. This really closely ties into intermolecular forces, so that's why this is a really nice chapter to tie in with that. Okay. Before we get started though, here's some basic terminology you should be aware of. You should know what a saturated solution is, unsaturated solution, supersaturated solution, and you should be familiar with the term solubility. I'm not going to read these to you. You can take these down if you want, but most of you should already know what these terms mean. You should also know what dilute and concentrated means. Again, I'm not going to, insult your intelligence by defining those. I think you guys pretty much are good with that. If not, go ahead and look it up in the book and ask some questions in class. But what we're going to look at when we measure concentrations, because the solutions can vary in concentration. That's the difference between a heterogeneous and a homogeneous mixture. Solutions are homogeneous mixtures where the solute is completely evenly distributed with the solvent, and therefore you get even mixing, and the composition is the same throughout. But because of the way solutions form, you can have more solute put into one solution. For example, you can have a salt solution that has a lot of salt in it. We would say that it's concentrated, and a solution with salt that's just a little bit in there, and therefore we would say that it's a dilute solution. So how do we measure those as opposed to just saying concentrated and dilute? We use what's known as molarity. You should know this one. We've talked quite a bit about this. I don't think I need to refer back to it, but if you need, again, if you need the review, let me know. Mole fraction is something we talked about in gases. Gases all readily mix together. There's no gases that will not mix together, and we'll see why that is when I start explaining the solution formation process. But what this is, X is the mole fraction. It tells you how much of one particular gas you have in your mixture. So for example, if I have a mixture of two gases, and let's say I just have helium and I have argon mixed together, what I want to know is what's the mole fraction of helium to argon. Well, what I would do is I'd figure out how many moles of helium I have and then put that over the total number of moles of helium and argon. What the mole fraction is, it really comes out to be the relative number of particles, or the relative percent. So it's kind of like a percentage without multiplying by 100. So if I had 50 of the helium and 50 of the argon, I would have half and half. So I would have 100 total, and I would have 50 helium over 100. I'd have 50% helium, so I would be multiplying by 0.5 to figure out what the ratio, or how much gas is in there. We talked about that in the gaslight chapter. So if you need to, go back and review. I want to focus more on the solution formation process. All right. So with solutions, when they form, there's a number of forces at work. So you've got this water. Okay, so let's say we have water in a container, and I put the solid substance in here. Let's say it's, I don't know, sodium chloride. Okay, well, there's a force holding that solid together, right? If I have sodium chloride, there's a force holding those sodium and chloride ions together. That would be the ionic bond. Okay, if this were a molecule, let's say sugar, you would have an intermolecular force holding those molecules together. So that's why it's important to talk about those attraction forces, because if I put carbon in here, then the attraction force would be covalent bonding. If I put copper metal in here, then it would be metallic bonding. Okay, so you've got to be careful with understanding the attraction forces that are in our solute. That's what this is: solute attraction force. Then in the water, there's the hydrogen bonding that's in the water molecule. So between two water molecules, you have what's known as hydrogen bonding. Okay, and that's the force going on from here to here. Okay, that's what holds water molecules together. So those solvent particles are held together with a intermolecular force. Something is holding these particles together. Well, if this is going to dissolve and go into solution, I have to break these two forces. So these forces have to be broken. So remember back when we talked about bond energies? In order to break a bond, I have to add energy. So therefore, if I'm going to break that solute, that's an endothermic process. Energy must be added to break the solute apart into pieces so that it can make room for the sodium ions to come into that place. But I also have to break my solvent solvent attraction forces have to be broken, and my solute attraction forces have to be broken. Now, as a result of that breaking, what happens is the sodium ion is then attracted to the negative on the oxygen. The chloride is attracted to the positive on the hydrogen. okay, in the water molecule. Now the water molecule stays intact. This doesn't break apart. This is a covalent bond and it's way too strong. It's never going to break in the solution process. But in the solution process, we break the intermolecular force, we break the ionic bond that's holding this together, and we form an ion dipole attraction force that is considered exothermic because we're creating a new bond. When these two come together, they create a bond and release energy out, and that's exothermic. So to figure out the overall change in enthalpy of the solution, what you do is you add up all three of these numbers. And if the third one, which is always our solute solvent, this is always the one that's exothermic, if this is greater than these other two, then we would know that our heat of solution would be negative. We would expect the process of solution formation to be exothermic. If these two are greater in force, then we would expect the solution to be endothermic because these are both endothermic processes while this is an exothermic, and we would have a positive change in enthalpy for the heat of solution or the enthalpy of solution. Okay, so the formation of so when we create a solution, we always have to have a change in energy. Either energy has to be absorbed or released. I'm going to show you a little video that will kind of do a better job of explaining what I'm talking about right here. So let me show you that video. What's called the dissolution of sodium chloride. Dissolution just means formation, making a solution. It's just a fancy way of saying a solution is forming. Alright, so if we look at this process here, what we can see happening is we've got the sodium chloride together, okay? Positive, negative attraction forces. Notice the chloride's a little bit bigger. And take a look at what's happening here. The hydrogen is being attracted to the negative charge. Negative charge attracts the hydrogens, while the positive is attracted to the oxygens. This process here of surrounding these ions is referred to as hydration. Hydration occurs as that is forming. So if we pause it right here, we can see that let's keep going. So you can see that the hydrogens are attracted to the negative anion, while the cation, the sodium ion, is attracted to the negative side of the water molecule. When the waters are surrounding the ions like this is called hydration. Now, if we go back just a second here and pause it, we can see that there's still an attraction force between the water molecules. The water molecules still attract each other, so there's a little bit of hydrogen bonding that's still going on. Now, if I back it up a little bit, what happens here is we're breaking this ionic bond, and as we break that ionic bond, they're also creating a new force. So this force right here is now our ion to dipole, in this case ion to hydrogen bonding force, and that force is exothermic, which overrides that endothermic process. Now actually in this water, in salt, we'll look at the numbers in just a second, that's actually a little misleading in the fact that it's not really exothermic for this process. I'll talk about that in just a second though. So if we take a look at the numbers here for sodium dissolving in water, the solute is the attraction force between the ions in our sodium chloride. The water has hydrogen bonding. We're not going to look at the value for this, and you don't really have to look at the numbers. It's not that important. What's important is you understand that this is endothermic, right? This is going to be positive change in enthalpy, as well as this is positive. These are those two that require energy in order to break. I have to break the hydrogen bonds, I have to break the sodium chloride bonds. So when the salt forms, and we look at the overall energy, oh, sorry, forgot about this one here. This would be my solute solvent. Notice that this is a very large number because that ion is strongly attracted to the water, and therefore we get a negative. So this is my exothermic process. Okay. So if I add all three of these together, notice what happens for sodium chloride. Formation of sodium chloride is slightly endothermic. Now remember, endothermic processes tend to not happen unless something else is going on. Remember, we want to know if something is happening. Hopefully you remember that the only way you know if something occurs is if you look at your free energy. So if we look at the free energy for this process, okay, and we plug this information in, we have our positive 3 that we put in here. Well, that's not going to make free energy negative. Remember, we want free energy to be negative. So what's the only thing that's causing, really not the only thing, but what's causing this water to dissolve the salt? It's going to be the entropy. So entropy is really the driving force behind this, because if we have the salt crystals, sodium chloride solid, well, there's a lot of order there. Water by itself, in a liquid phase, there's more order there. But if I can take these ions and spread them out throughout the water, there's more disorder in that system. So it's going from order to disorder. So when sodium chloride's solid, goes into ions, that's increasing the entropy of the system. And therefore, if the entropy of the system is increasing, that's always going to be positive. So therefore, we're going to have a negative with a positive in here. That will then override my change in enthalpy, making the overall process negative. Now also take a look at temperature. Temperature has an effect as well. Think about what happens if you increase temperature. If you increase the temperature, would you cause something to dissolve more, or would you cause it to dissolve less? You'd cause it to dissolve more. So higher temperatures tend to increase the entropy by providing more disorder in the system, which then continues to override the enthalpy, making it overall negative. So the moral of the story here is that entropy has a huge effect on solution formation. But keep in mind the three types of forces that are in here. You don't have to worry about the numbers, you just have to worry about understanding which ones are breaking with the intermolecular forces and which ones are being formed, again, with intermolecular forces. So we can explain why oil doesn't mix with water. Oil has London dispersion forces. Now, because the molecule of oil is large, that London dispersion force is going to be pretty strong within it. Okay, so it's going to have a relatively strong London dispersion force. Now, water has hydrogen bonding. Well, if this is nonpolar and this is polar, there's no attraction between the water and the oil. They don't really have any attraction force. So our solute-solvent force is going to be very small. Now, it attracts a little bit because you know London dispersion forces are slightly positive and negative, and hydrogen bonding is slightly positive, or very positive and very negative. But it's just not a very strong attraction force. So therefore, when we add up all three of these, the strong intermolecular force of the oil and its intermolecular force of the water keep these two from forming, and therefore they're never going to form a solution. So in salts, you can see the hydration effect here occurs. The ions surrounded by the negative water, and then the positive hydrogen ions surround the anion. And the same thing goes on with, the opposite goes on here. Water is not attracted too much to the oil, so therefore the oil will stay in here. So entropy should cause this to dissolve in here, right? Entropy, it would be better if we could have these all separated and spread throughout, but that's not going to happen because the intermolecular forces here and here don't merge together. So this gives us the last slide, which is going to summarize everything we just said. I guess it would be me. So if I have a polar solute and a polar solvent, there's a large attraction force between the solute-solute, a large attraction force between the solvent-solvent, and a very large solute-solvent attraction force. And when I calculate my change in enthalpy for the solution, I get a very small value. So therefore my solution forms. Okay. Now if I look at the polar solute and a nonpolar solvent, then the attraction force in the solute is large, the solvent is relatively small, and the solute-solvent tends to be very small as well. And what you have is a very large positive value for your change in solution because there's not much attraction. This isn't overriding these two forces. So therefore, no solution forms. Okay. If this is a polar solute, yeah, that's right. Okay, polar solutes have a very large attraction force. Okay, I was thinking something else. Sorry. Nonpolar solute, nonpolar solvent. Small attraction, very small solute-solute. Therefore, this doesn't need a lot of energy to overcome this, and therefore this is small for the change in enthalpy of solution, and our solution forms. And I think you can see what's going on when the nonpolar and the polar solvent. Again, no solution forms. So here is the moral of all of this, is that if our solute and solvent have very similar forces within them, polar and polar and nonpolar, then our solutions will form. This is where we get that term like dissolves like. I can't spell dissolves, but dissolves. I can't write for some reason on this thing. Dissolves like. What that means is if the intermolecular forces are very similar to each other, the particles can't distinguish between them and they just merge together. And that's why all gases dissolve within each other, because there's really the intermolecular forces are ignored and nothing is holding those particles back from just completely dissolving into each other. So that should be enough information to get you started. Like I said, I'll do one more video on factors that will affect this, because obviously there's things that can change this basic idea. But that's pretty much it. So I will see you in the next video.